oxidize this in air, the carbon's going to oxidize and go off as CO2. It's going to leave the sample as the gas. So you wouldn't expect very much carbon to remain behind. It's only that which could not gain contact with the air, the oxygen in the air. That's all. That's why there's any in there at all. If you had stirred this and mixed it well, the carbon would be gone.
I have
you-
a project that I'm working on right now because, like I said, this is my hobby part of it, the metals and trying to figure out what's going on and the algae, and because there's a considerably more material here than there is, even considering if the electrodes were right, or even the original weight of the electrodes. The total mass in general, the weight of the mass, right? Regardless if there's metal and stuff. And I know that I'm doing this crude in the open air furnace with a torch and some other things. I do have vacuum furnaces, so they just don't get hot enough. They get hot enough to do other things, which would be later on. I could send you samples, you could look at them. But I know I need a hot vacuum furnace to kind of get where I need to go. But on this subject, I have a customer that is looking for biomass. They're looking for carbon, and they need carbon. They need a biological way to get carbon. If I can grow enough biomass, which I can, I had just purchased a vacuum furnace, but it's a low temperature one. Can't wait when I get back to go fire it up. I checked it and I bought it used. It'll go to the first stage of torrefication for them, which is 300 degrees Celsius under vacuum. And so then I'll be able to see how much carbon I can pull out of it. If I get a significant amount of carbon, you're right, it doesn't go to CO2, then that's a product from it.
Well, now wait a minute. One of the problems is that my vocabulary and your vocabulary don't match very well. And that makes it a little hard for me to understand what you're saying.
Mm-hmm.
When you're talking about carbon, it really matters the chemical form. So when you say they want carbon, what do they want? As an oil, or they want it as something they can burn, a lubricant? What?
Oh, they're using the carbon to add it to steel, to iron to make steel. So what they do is they take coal and they put it in their blast furnaces and turn it into coke. Once they then turn it into coke, then they pour it into their iron and they make steel.
Okay.
So they're getting their carbon from coal, from plant material, green waste, whatever they get their hands on right now.
Right, metallurgical coal is another kind of coal that's used for the refining of iron, and it's called metallurgical coal because it's very, very pure. It doesn't have a lot of these extra elements in it that they don't want.
Mm-hmm. This is exactly right. I don't have their samples that they're sending. They're supposed to be here when I get back, so I know exactly how pure their material is to see if I can match that purity.
Right. See, now carbon occurs very, very pure as graphite.
Mm-hmm.
The only trouble is that graphite is very, very expensive because it has other uses.
Yeah.
But if you want to get really pure carbon, that's where you go. Now, if you want to get really, really pure carbon, you decompose something with carbon in it. For example, you can decompose propane or natural gas, methane. You can decompose those into carbon. The only trouble is it's far more expensive than coal.
I've never heard of that process. Give me a summary of that.
Oh, it's very easy. I mean, the easiest thing, you can see it happen if you wanted to. You just take a flame and you burn it without oxygen and you get soot. And you've probably done that.
Okay, yeah.
Well, that soot's pure carbon.
Oh, okay. Thank you for the aha moment, but yeah, you're right.
Right. So it's very simple. The only problem is that the cost of the natural gas far exceeds the value of the carbon for that particular purpose. If you're going to use it to make graphene or something like that, oh wow, this is fantastic. But to use it for metallurgical refining of iron on a multi-trillion-dollar ton scale, it's not practical.
Of course. Okay.
And anything you make will not be practical because you have to use too much energy. I mean, the scale of iron purification is so huge, the amount of carbon is so huge, and the cost of the iron is so small that it just isn't practical to use anything that requires any energy to make. So they mine metallurgical coal, which is running out because it's a rare form of coal, so they have to use less pure. Well, then that introduces impurities into the iron, which they have to take out other ways.
Yeah.
And that's the slag. Mm-hmm. Those are the impurities that come from that process, and they throw all kinds of other crap in there to capture those elements and bring them to the surface, which then they take off as slag, and they grind it up and they put it on our roads instead of sand. Mm-hmm. That's that red stuff that you see when you came up the road. That's slag.
I saw that you had a metal plant there. One of the issues that these large steel mills are looking at is taking green waste from farming operations and stuff and putting them through the pyrolysis process to make their coal.
Yes, you can do that. I mean, that's what they used to do with trees, and they used to make charcoal out of trees, and then the charcoal was then used for various purposes, usually for burning or some type of refining.
They've come to the conclusion that even though there's an energy input there, it's still profitable to them to do that.
As long as the material is a throwaway, or the only problem is that you can also use it to make ethanol, and you can use it to make methane, which have a higher value. So
yeah, all that is very much true. This particular steel plant needs carbon. They don't care about anything else. That's what they need, is they need carbon.
That's right. They absolutely need carbon. There's no doubt about it. But they need it cheap enough that they can afford to buy it and still sell the steel at a reasonable price. And so it is not, the issue is not the availability, it's the cost. Carbon is very easily available. I mean, it's all over the place.
Their issue is they have hopefully that was turned up the right direction to see that little piece of, we'll find out. If it wasn't turned the right direction, then we're not going to see that piece. This is where they're mandated to use a biological carbon, not a ground carbon.
Dr. Storm, are you familiar with the impedance of the graphene using carbon rods in radio, crystal radio, in the electric field, in grounding the field or partially impeding the field, creating a stronger wave attenuation?
You have to give me a context there. I mean, I'm not quite sure I understand.
In setting up a crystal radio set, okay?
Yeah.
Using a pyrite, you take a piece of carbon and you would have to I would use different carbons in different amounts and get a different wave generation.
Yeah, I mean, you can buy them now, but back in the days when I made crystal radios, they weren't so handy, and so you make your own by using a piece of carbon. In fact, as many resistors are made from carbon that way, but they're done professionally. But yeah, but I guess what's the question?
I called trying to figure out the formula to figure the impedance of carbon, I called the manufacturer of the carbon rods and had a long discussion with them, and the basic understanding was they put it into an oven and they cooked the carbon until a graphite or graphene. So the graphene's very expensive because it takes a lot of energy to make graphene out of carbon, and graphite was the element before graphene, and then carbon, and it was depending on how much time they had, what size rod, and the formula behind that,
Right.
that they kept it in the oven to create
That
a certain
changes the
amount of
resistance,
impedance.
Well, when you use the word impedance, you see that has a different meaning than resistance. Impedance is the resistance to an alternating current. Resistance is the resistance to a steady DC current. And the two are generally mixed together because you use a resistor and you measure its resistance using a ohm meter. That's its resistance. Its impedance will be different than that depending upon the frequency of the wave passing through it. So you want to use the word resistor or resistance because that's the more general term. Since it's
Okay.
measured that way. But impedance has a different meaning.
I'm glad you explained that because that was more or less my question.
Yeah.
That was confusing.
Right. For example, you can have a coil of wire that has a very low resistance to DC, but a very high impedance. In other words, it will resist the passage of AC, and that's called an inductor. And that's what you very frequently find is these little coils of wire in radios.
Right.
We just loaded tons of coil wire.
Yes.
Yeah, those allow the DC to pass through fairly readily, but they stop the flow of AC. And the resistance to AC is called impedance. That's what
Okay.
and it's measured in ohms. So it's measured the same way as resistance is measured, so you usually get them confused. But it's applied only to AC.
Very good.
Okay, so anyway, so here's the stuff, and we're building up some statistics here. This is mostly oxygen.
Did we? I don't know.
And look at the huge oxygen peak there. Mostly oxygen. It's not giving off much in the way of X-rays, so it's taking a while to build up. But let's get rid of some of these that are not there. We don't have any copper now. We have a little bit of nickel, iron, chromium, calcium again, a lot of sulfur, so it's similar to that of the sample, some silicon. Let's see what this stuff is here. Oh, we got aluminum, magnesium, a little bit, a lot of sodium. So this is mostly sodium and oxygen. In other words, it's a flux.
Sodium metal.
Sodium metal and oxygen is highly oxidized. I mean, if it's sodium metal, it will react with air very rapidly. I mean, if you say this is slowly reacting, it could very well be that there's sodium metal in it, and that's reacting with sodium oxide.
How do they make sodium metal to begin with?
Sodium metal is not easy to make because it's so reactive. It's reactive to water, it's reactive to air, it's reactive to almost everything except metals. So I don't know that you would conveniently, you'd be able to make sodium metal. It's normally made by electrolysis of molten salt. If you take sodium chloride and melt it in the absence of water and everything, so you have to heat it up to maybe 400 degrees or something like that, centigrade. Put electrodes in it, you can separate out the chlorine from the sodium, and you can make sodium metal and get chlorine gas as a consequence.
And they just pour it out of or they draw it out of the bottom of the vat somehow.
Well, the sodium, I think the sodium floats on the surface and you can then ladle it out. It's usually done in big vats. The chlorine's going off and collected and bottled for use for all kinds of chemical reactions. And then the sodium is ladled off, and then more sodium chloride dump in. So the sodium chloride and the sodium separate, and you can separate them physically.
Yeah, I've seen these videos where they have these long bars of sodium metal. You chop it off sort of Tootsie Rolls. You put it in packages. Just never knew how they made it. It's interesting.
Well, sodium metal, you cannot expose it to air.
Yeah, they package it right away.
Oh yeah, package it right away. It's usually stored under oil in order to keep it from reacting. But it's got to be stored out of contact with air, with water, and oxygen. It will react very, very quickly to both of them. In water, it reacts explosively, rapidly. You drop sodium in the water and boom.
Right. Well, then they had made hydrogen cells and ran trucks off of them years ago. They had these reactors, and they dropped the sodium in and ran the truck off of hydrogen fuel.
Yeah, you can do that. It's fairly dangerous. You have to be very, very careful. But yes, sodium when it reacts,
It didn't
with water
last
makes
long.
hydrogen. But it takes more energy to make the sodium than you get back from burning the hydrogen.
Okay.
So it's not a very effective way of, not a very effective fuel.
Okay, but do we know what direction this sample was facing?
It was, well, I can show it to you. Hang on a second. What it looks like.
Alright, so we're hitting the spot, so that's sodium metal of some sort, or sodium oxide or something.
It's sodium oxide. I mean, it's
That
not
is
going to be
true.
sodium metal out in the air, and you have a huge oxygen peak here, which is undoubtedly along with that. Let's see.
See, I've always known that the oxygen is the devil in this process.
78% oxygen,
Wow.
Wow.
10% sodium.
Now, what kind of oxygen is that? Is that a liquid oxygen or a hard?
It's a compound, sodium oxide. it's various compounds. I mean, you have.
Well, I can tell you this particular firing, to get the heat up to the highest I need to get it, I use a lot of oxygen. I forced a lot of oxygen into it even to get the balls of precipitate that you can see in the flux. And so, that's very, very interesting.
I mean, sodium oxide is used as a flux. It's used as a flux in welding. It's used as a flux because it melts at a fairly low temperature. It's inert. It will form a liquid that will cover things, keeping oxygen away from whatever you're doing, and therefore it's very convenient.
That's exactly what I see when I melt this, like I said, this particular experimental path. When I melt it, it's gonna get hot. It has to get really, really smoking hot. I mean, the crucible is red cherry hot, the top, bottom. I mean, I have a torch. The torch is about this long, and I've got a 1/4-inch nozzle behind the torch. I mean, I'm blowing a flame into this thing like this long. Serious. And I've got a bottom heater as well with a big 2-inch burner on it that's heating the bottom of the crucible at the same time to get the temperature into it. And it's amazing how much temperature it can hold and how much it can take to get it to precipitate into these little balls of metal here, or little balls of identifiable stuff. And that's what's interesting. Like the picture I showed you, that was a nice big button, but that button decayed within an hour from what you saw it. down into like a powder. It just fell apart on its own. I scooped it up and I put it in a little vat with some water to see if it would react with the water. Didn't react with the water, it just stayed at the bottom of the container. And so this particular hobby, it just shows me different paths of doing different things.
Well, one of the things that you really need is a background in chemistry. And because
I can figure out chemistry, the problem is I don't have any way of understanding what I have. This is the first time I've been able to see this particular samples in something that's quantifiable, so I know what I have.
yeah, right. I mean, what you're doing is a variation of standard chemistry.
Mm-hmm.
Now, you may be doing things to it that are non-standard, and you're therefore getting unexpected results. But the chemistry of these materials is really well known. I mean, these are industrial materials, things that are done on a large scale. I mean, this slag is made by millions of tons normally. So there's a huge amount of information that's known. Now, before you try to interpret what you're doing, you've got to know that, to know whether or not you're doing something different than that. And if you're doing something weird, it's only weird because it's outside of what's already known. But if you don't know what's already known, you don't know what's outside of that. And what I'm seeing here is this is well within what's known. I don't see anything unusual here.
Sure.
So, that being the case, you're sort of wasting your time if you think that you're doing something really novel.
No, I'm not wasting my time because what I'm learning is, okay, I have a whole list of things that I know. That I know exactly what they are. And this is just one more thing. Okay, this particular process gave me this result. Simple as that. Is it the same way the big boys do it? Maybe, maybe not. But this gave me this result. And I put it on a checklist. And I just go down this massive checklist. I've got 30,000 plus hours of checklist and documentation of different processes to get different results. Some are straightforward, textbook. Some are kind of, unique. Some are completely fascinating. We've done the same things, not this particular melting process and what we're doing right now, but I've done the same protocol and my things with painting other metals. And so that part of it I get. It's very difficult to hold the metals where they need to be. It's just a very difficult, that's why it's a hobby. It's not for sale, and
as a hobby, we all have these fun things we do.
Mm-hmm.
Yeah,
it's kind of relieves my stress when I get out of work. I go grab a torch and it burns something.
It's always fun.
It
Play
is.
with these things, and it's a good education.
Well, let's check a couple of these other samples if we could.
They're all the same. They're going to be the same.
They're going to be the same?
They're
Okay.
be the same because that was about the cleanest, but no, that one's the same. And I had hypothesized before I came here that this could be a sodium metal or a sodium oxide or sodium something, but I wasn't sure because I had no way of testing. I could just kind of think maybe it was the way it deteriorated in oxygen is what kind of led me to it.
Dr. Storm, is there a way that you can save the readout on that particular button there and then compare it to other stuff that he sends in the future to see?
You can have some samples.
Yeah, I can save this.
It's just interesting how.
So that what I'm saying is if you use other processes and then elaborate on the process of, and maybe get it better in the future, then we can do an analysis, proper analysis of a process.
Okay, what do we call this?
Dave Puck does.
What do you want to call this?
David. Sample 1, because I'll know what it is. See, it's just knowing what you make instantly right after you mess around can save you thousands of hours of trial and error.
Oh, heck yeah.
Okay, now here's another spot, different spot on there, which has the same stuff in it. This spot had,
It's got a spike of magnesium in it.
yeah. See that dark spot right there? That's what I'm looking at. Everything else is bright, which says that it emits electrons much better. This spot doesn't emit electrons very well. So it's got a different chemical nature to it. But it's essentially the same stuff. I don't see anything.
You know what we didn't look at, which would be great if we could do one more sample? Is figure out what that white stuff is on the outside of that bar. Will it figure that out?
That's what the sodium and the oxygen is.
No, he's looking at the inside sample, the little button. But you know the one that's oxide out there, that white stuff?
Okay.
Figure out what that is. So we can get to the bottom of that. Because it's interesting about that, even though it oxides, you know.
Will you have some of it?
Yeah,
Someplace?
that piece.
Let's get that done and call it quits here.
Yeah, I would really appreciate that.
What do you think about that? How do you think that electronic field comes to bear?
I don't know how to explain what he's reported. Neither does anybody else, as far as I can tell. So I don't know how to comment on it. I think he's probably seen real phenomena. Some of it's been very, very strange. But I have absolutely, it's not the area that I've spent any time studying to try to understand.
Understand.
I mean, if you ask me anything about cold fusion, I tell you anything that anybody knows. But his work I have not followed in detail, so I can't comment.
Well, my main subject to be here is to talk about cold fusion. I want to get to the
Can we
bottom.
make this, it's a little thick.
Okay.
Can you scrape that off of it?
Maybe
Take that.
let's see, maybe I can put that in there, let's see.
Or if you have a slide, I could scrape that stuff off. Why is with oxide? It's really weird. That's probably enough, right?
Yeah.
So how long have you been studying cold fusion?
25 years.
How many?
I was at Los Alamos when Tom and Fleischman made their original announcement. We got money from the DOE to study it, and so I was one of the ones that used that money to study the effect.
Wow.
And got positive results. But nobody believed it. So
How long did the reaction?
You got positive results.
I had positive results there. We started off making tritium using the technique. And then I got money, internal money, to make, to look for excess energy. And we're successful in doing that. So we replicated Pons and Fleischmann. And then when I set up the laboratory here, I studied all the different aspects of it, and also replicated it numerous times. So but I've written 2 books on the subject. So, you know,
Do you have any books with you here?
Yeah,
Can I buy one?
yeah,
Can I get it signed?
yeah,
So you'll sign my book for me, Chet?
And me
And I'll
too.
sign yours?
yeah.
Will you sign our books?
Yes,
I'm just messing
I would
with you.
love to.
I would be very honored.
Yeah, I can sell you the newest book. I don't have copies of the first book that was done in 2007.
The new one doesn't have the latest.
The new one has a
understanding.
theory and a lot of new information in it. It discusses the important observations. It discusses what other people have, how they tried to explain it, and it explains my theory. Which
I like the very end of your subject because when you said if you're going to dive into this subject, you need to throw everybody's theories out and start with your own findings, and then work backward and see where they fit in the ballpark. Because that's pretty. It's pretty much my undertaking of what I do. Is I just go at it myself and figure out, and then when I feel that I need to look for validations, I go back the other way and say, okay, I'll find guys like you to do stuff like this. All right, cool. But if I went out to try to make sodium oxide, I'd be, if that was what my goal was, I would be lost. I wouldn't have to do it. Now that I know what the process was I did, if it's conventional, fine. If it's unconventional, that's fine. It doesn't matter to me. It just matters to me that, okay, like we said earlier, there's a checklist. And there's an understanding. And just put that in your book. So, cold fusion for me is it's a pretty interesting subject.
Let me ask this question first. Can you explain to us exactly what cold fusion is?
Yeah. Well, I can tell you what it does.
By the end of today?
Yeah, oh yeah, no. Fusion, by definition, are 2 nuclei coming together to make a 3rd nuclei. And it turns out that you can bring 2 nuclei of deuterium together, and when you do that, they will fuse, make a tremendous amount of energy, and make a 3rd nuclei. Now, there's 2 kinds of fusion. There's hot